conservation of energy question from the Nelson Physics 12 textbook. It is basically a review of last year when you're looking at conversions between kinetic and gravitational potential energy with no friction coming into the picture. The situation here is a pendulum. You're given the length of the string of the pendulum. It's being held out to the side here with an amplitude of 24.5 centimeters. Now with the pendulum, the amplitude is the horizontal distance here. It's not the angle to distance. It's being measured side to side. Now, neglecting friction and air resistance, what will be the maximum speed of this pendulum? That's the question that we're asked to solve, and we're going to use conservation of energy. Now, the maximum speed of the pendulum will be at the bottom of its swing. You should be familiar with that idea from conservation of energy questions you did last year, that where the gravitational potential energy is lowest, the kinetic energy will be highest, and therefore that will be the greatest speed. So in solving this, the first thing we will do is draw a system diagram and get all our givens into place. Make sure we know where the significant positions are that we're trying to solve for. So we have got the diagram from the textbook here. It's not big enough to work with. So I'll draw that. And then the other position, straight up and down. I'm trying to draw that the same length as the other. So we'll identify these as position A and B, and we'll write down what we know, what we need to find out for each of these. So B is the lowest position in the situation we have here. So we'll say the height is 0 there. That's the most convenient thing to do generally, is to say h equals 0 at your lowest position. And the speed at B is the unknown that we're trying to find out. Now over here at A, it's being held at rest before we let go, so V is 0, and the height is, how high is this relative to B? We're not given that information exactly. We're going to have to work a little bit to figure that out. So before we can carry on, we have a little bit of work to do. The thing we want to solve for is that difference in height, and we're going to do it with just a little bit of math. Okay. Given some of the measurements from the diagram, the length of the pendulum string and how far out it's being held, amplitude of 24.5 centimeters. Our strategy here is going to be to find the third side of this right angle triangle. We'll call it x, and then we can figure out the height here just by subtracting that x from the length of the pendulum, the 85.5 centimeters. So it is a right angle triangle, so we can use Pythagorean theorem. X squared plus 24.5 centimeters squared is your hypotenuse squared. And if you solve that, x will turn out to be 81.91 centimeters. Then our height at position A is 85.5 centimeters minus 81.91 centimeters. .59 centimeters. Now I want to stop here to make a point about significant digits. All the quantities in the problem were given with 3, and so you'd expect in the end that you should have 3 significant digits. That's actually not the case in this question, and the reason is because of the rule for adding, subtracting. we have subtraction here. The rule that comes into play is that when you add or subtract, your precision in the answer is determined by the fewest number of decimal places. So because this 85.5 centimeters is just to one decimal place, you cannot expect the result of subtraction to be precise to any more than one decimal place. So that is, in this 3.59 centimeters, only your 3 and your 5 are significant. We'll keep the other to prevent rounding errors, but we have lost significance, and we're only going to have 2 significant digits in our answer. That's just a weird thing that happens sometime. Your textbook reports the answer to 3 significant digits. They're wrong, but we can live with that. Okay, so our height, I'm going to change it to meters because I don't want to accidentally subtract the wrong units later. All right, so we're set up pretty well. Next step is to do our energy bar diagrams, our LOL. Need room for lots of bars. So we start by identifying our system. Our system includes, of course, the pendulum bob, but also because there's a change in height, the reason for that is the interaction with the Earth. Now, by making the Earth part of our system, we don't have to do calculations of work done on the bob. We can take care of it by having a gravitational potential energy bar on our LOL diagram. Okay. So our energy bars, we have EG, EG plus EK makes the total mechanical energy. In the first position, there's A. We have no kinetic energy because V is 0. And the gravitational potential energy is equal to the total mechanical energy. There's no work done on the system by outside forces, so the final final total energy will be the same, but now it's 0 EG, and all of that is kinetic energy. So, starting position, all gravitational potential energy you let go. In the lowest position, it's all been converted into kinetic energy, so you'll have your maximum speed down there. With a clear LOL diagram, it's no problem then to write your energy equation. Your total energy at A is equal to the total energy at B. At A, it's all gravitational potential energy. At B, it's all kinetic energy. Gravitational potential energy is mg times the height at A. The kinetic energy is a half mv at B squared. Your masses cancel. So let's substitute in 9.81 meters per second square. The height at A, we went to some work to find that earlier. 0.0359 meters is equal to 1/2 times VB squared. And VB works out to be 0.84 meters per second. As I mentioned earlier, we're just going to report that to 2 significant digits. And we can say, therefore, the maximum speed of the pendulum is 0.84 meters per second. To review then, I can't emphasize enough how important it is to have a good system diagram, a nice big one where you can do math if you need to, and you write down what's given, you write down what you need to solve for. This is where you organize all your information. Once that's set up, you move to your energy bar diagrams, identify your system and the energy before and after. There you go. And once your LOL diagram is set up, you head straight into your energy equation, and the solving is fairly simple from that point on. So that's how it works. Good luck with your own.